All right, people, this is kind of like a follow-up to our first sort of look at section 2.5 scatter plots. This is something that we might uh, be doing like in class. I might like kind of, if I can put you in groups and try some of these examples and then go over them. There's a lot of like repeat instructions from the original 2.5 notes, but there's some other things that I want to address that could like rear its ugly head. So, but first, some kind of warm-up lead-in questions that are kind of related to what we've been doing and what we're going to kind of do again with scatter plots. If you wanted, as it says, to write an equation for a line, what would you want to know about the line? What would you need to know about the line? Or what would you want to know about the line if you were supposed to be giving the equation of said line? What would you need to know? Think fast. What would you want to know about the line if you needed to write the equation? How can you figure out the slope of the line? Because you might have been thinking slope. Okay? I need to know the slope of my line in order to write the equation. Well, okay, how can you figure out the slope of a line? And then what are the ways to make a prediction about a certain x value, especially a future x value that might be even like off the page, off the screen? Again, we've already covered this in like the original 2.5 lesson or talk or video. But so again, some of these things we're going to kind of cover again and just kind of reiterate again. But there are some new things that I want you to be aware of, some things that might trip you up potentially or whatever. But so here we go. Remember, if you're plotting your own points, drawing your own line, picking your own points, etc., at the end of the day, your slope, your equation, your predictions are just going to be estimations. So like I said last time, so pick your points as far apart as possible. And that'll help your estimation be the best estimation it can be. And then if you have specific points that you know are on your line for sure, then everything can be exact. Especially if you are given your line of best fit, like if it was drawn for you, by a computer or something, and you knew that the line that was drawn through your points was like the perfect line of best fit, and you happen to know that there was like specific points that were definitely on that line, then your slope and your equation and your predictions, those are going to be now considered exact, But for the most part, especially if you're drawing your own line and stuff and you're picking your own points, you're guessing, oh, this point looks like it's on the line. At the end of the day, it's all going to be estimation, but whatever. So here's the paper. Here's the paper that you have. So in class, I hope you probably tried these first, but so this one is about the number of people in a group compared with the escape time, for like an escape room. Okay, so the question is, predict how long it would take a group of 10 people to escape the room. Does it matter that there is already a data point for 10 people? So here's the theory here, okay? There's already a data point right there. So it looks like as part of the survey or as part of like the data collecting, it looks like there was a group of 10 people that took, just about 12 minutes, maybe just under 12 minutes to escape the escape room, okay? So, but if you had to predict how long it would take for a group of 10 people, you're not going to go with like that point, because that was just like one group. But if another group of 10 people came in and you had to predict how long, it would take that group of 10, you wouldn't go with 12-ish. You'd go with the point on the line, like right there. Okay? And so your answer would actually be 6, 7, 8. Does that make sense? I hope it does. Again, like you're making a prediction on like the next group of 10, This was just one point of many that sort of like averaged out to your overall line that helps you make predictions. So if you had to predict for like, 10 people, you'd actually go with that spot right there. And so your final answer is going to be Jeez, my board had a spasm there. So you're going to say like 8 minutes, And, that question is officially answered. But if you wanted to do this the really fancy way, you could actually make an equation. Like I picked those 2 points. Remember, the farther apart the better. And you would figure out your... Remember, one of the questions back here was saying, like, how can you figure out the slope of your line? Well, I mean, I guess you could... like, if you're just eyeballing this line, you can, like, count boxes. You know what I'm saying? I mean, we'll talk about that more in a minute. But, one way to get your slope is to kind of eyeball it and count the rise and the run. But really, using this actual formula from actual coordinate values, x and y values, that's going to be ultimately, spoiler alert, that's going to be the most reliable recommended method from me. Okay, so there's our slope, 20 over negative 8, which I guess is negative 5 halves, or that's a nice decimal, negative 2.5. And then once you have your m, you can take one of your 2 points along with your m value, plug it into point slope form. Again, nothing new here. There's a few things new I said I want to teach you. There's been nothing that new yet. And then if you needed your equation, or if you were going to, answer this question using your equation, here's your equation. And then you could like literally replace the x with 10, because x is a number of people. So you could now like plug in 10 for x, and it looks like you should end up with, you should end up getting 8 again, but bottom line is the final answer is 8. And once again, like nothing that new so far. You can do the fancy equation way, but for this problem, people, I mean, honestly, if they're asking for like 10, or let's say they were asking about, gosh, 1, 2, 3, like, if they were asking about a group of 4, or a group of 5, or a group of 3, or a group of 7, whatever. Like anything that you can just kind of like eyeball up on your line, and you're making a prediction, that's like so easy just by like using your graph, okay? You don't really have to use the equation, Yeah, I mean, I might as well include this, sorry, I'm going to mention one other thing too, right? Because sometimes you can like be a little bit, I don't know, confused, or you might find it weird that, I could ask you the question, what about a group of 15? According to this data, right, and according to our trend line, how long would it take a group of 15 people to escape? And you kind of like go on your line and you realize, Mr. Falk, my data, my line says that it would be like negative minutes. Like, look, the point for 15 would be down here, which would correspond with like a negative time, which doesn't make any sense. So, it's just, that's kind of a good lesson of, data sometimes only makes sense for like certain, domains, like certain intervals of like values, you know what I mean? Obviously, at some point this data stops making sense, because it's literally impossible to escape the room in like, negative 4 minutes, so so this next question that I wanted you to learn something about says, predict the total strikeouts for a pitcher who's pitched 36 games. 36 games. So I would argue that for this particular number, it's not like they're asking for 20. Look, if they were asking about 20 games, you could probably, accomplish this just by kind of eyeballing, where this was going to like hit the line, like where, if this line kept going, where would the dot be for 20 games? For 36 games, that's probably like off the page, off the screen, whatever. And you could kind of find a rate, like I mentioned last time, or what I'm going to usually pretty much have you do and want you to do and recommend you do is come up with the equation. Okay? So again, I don't want to like spend too much time covering the same stuff over and over again. Nothing new. Here would be some points I would pick. Okay? And therefore my slope would end up being 11 over 4, or actually that would be a nice decimal as well. We're getting pretty lucky here with these nice. That would be what, like 3.75? But anyway, here's where I want to make a new point for you, no pun intended. I want to share something new with you that I want you to kind of like try to understand. So, obviously, when you set your mind to like writing the equation, you needed to figure out the slope. So again, back here it was all about, how am I going to figure out the slope? Like back here, how can you figure out the slope of a line? And I was saying like, well, you could like use the formula, or you could like kind of count your rise and your run, like count some boxes on the graph. But, trying to be quick here about it, I don't want to, drag this out. What I'm saying is, take a look at this particular example, and what if I said, figure out the slope by counting from this point to this point, count off your rise and count off your run, and do it that way. You, in this situation, along with a lot of situations and examples, you run the risk of making a mistake. Because here, check it out. If you were sort of like not really paying enough attention, and you go, okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. My rise is 11, and my run is 1, 2, 3, 4, 5, 6, 7, 8. Yeah? So is your rise over run 11 over 8? No. The formula will always be correct. You know what happened here? You might have already noticed what I was trying to, point out to you. Look here on the green. When I counted 1, 2, 3, 4, 5, I was making a grave error. Because every one of these boxes is not one strikeout, it's 2. the way this vertical axis is being scaled, it's being scaled by 2's. It doesn't go 1, 2, 3, 4, 5. It goes 2, 4, 6, 8, 10. So, you'd have to keep that in mind if you were going to like count off your rise and your run. And that's why, okay, so I'm finally finishing my point here. That's why I say identifying this point, 3, 20, and 11, 42, and then just kind of going with your formula, I highly recommend you just do that every time, because then you're not ever going to like make the mistake of counting wrong because your axes might be scaled weird. So that's my first new thing that gets sort of exposed doing these examples. But you figure out your slope, blah, 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 blah. And then once you have your equation, don't forget, you can now plug in 36 for, is it X or Y in this case? 36 games. So you'd be plugging it in for X. Okay, you'd plug in 36 for X. So what's that going to be? Number 11/4 is just like 3.75, I believe. So 3.75 times 36 plus 11. Hope I'm not wrong about this, but it looks like you can say 146.75 strikeouts. Now this one, we have another plot twist here. Predict the number of customers on a 25-degree day. So once again, you see how these are scaled? Looks like here it's going by tens. 50, 60, 70, 80, 90, 100. Down here, ooh, this is ugly, isn't it? That's 50. That's 55. So along the bottom, it looks like every square is 2.5. That's ugly, I guess. So what I'm saying is, it's again like you probably don't want to figure out your slope by counting the boxes. What you want to do again, and this is what I'm recommending like every time, is identify a couple points. The farther apart the better. Looks like I just went with like literally one of the black dots there, 60, 100, and then like this one. Was there like another one? Maybe there. I wouldn't have blamed you for using that point right there. But anyway, the bottom line is you pick a couple of points that look really good to you, and you find your slope that way. Okay, again, nothing new about that except me reminding you that the formula is way more reliable than counting, because you might forget that it's not always just 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3, 4, 5, 6. Okay, so the formula will never be fooled. And so here it looks like our slope is 16 over 5 or 3.2. If you wanted to go with a decimal, 3.2. Yeah, I think that's right. So anyway, here's my second big new thing. Ready? All this time, I hate to kind of regress back, and take like a bunch of steps backwards, but all this time, check this out. Going back to, I think this was the first example. Once you had your M, okay, we used this formula, right? We used that formula. But I don't want you to forget that if you are literally looking at your line, using this formula, plugging in your M and a point, it's not the only way to get your line. In theory, you can do y equals mx plus b. If you're literally looking at the graph of a line, if you can figure out m, and don't forget what b is. What's b? What's the b in y equals mx plus b? I hope to, hope to God that you remembered that, your b is your y-intercept. So if you're able, okay, like if you're on your toes about this, right, if you can remember that just by like looking at your line, if you can actually tell with a lot of accuracy where your line is going to hit the y-axis, that's your b value. And it looks like here, if you were able to tell all along that this line was going to intercept your y-axis at 33, you could have saved yourself 2 or 3 steps here. So again, I hate to kind of go back on my, on like what steps I was teaching you, but I don't know. I just like to tell the full story. At the end of the day, spoiler alert, I'm still going to highly recommend you use this formula. I'll reveal that in a second, but just don't forget that, hey, sometimes if you're careful about it and you got like a good eye for it, you can actually just plug in your m value and your b value, like whatever your y-intercept appears to be, into this formula. But here's why I almost say like, actually, never mind. But because here, check this out. People, you could look at this particular example. So back to the daily customers and the average temperature. And you could go, all right, so look, okay, I got this point and I got that point, yada, yada, yada. Here's my m value, 3.2. Like, oh my goodness, but look, it looks like my line is going to intercept the y-axis at like, I don't know, 40, 30, 20, maybe like about 15, I don't know, whatever, 15-ish. That appears to be my y-intercept. So why don't I just say y equals mx plus b? Why don't I just say that it's 3.2x plus 15? I mean, it appears that my y-intercept is going to be, I don't know, 15, 16, 17-ish. Because guess what, people? No. Or, no. No. Because look, see this? See this right here? This means we skipped a whole chunk of x-axis, meaning the y-axis, okay, and therefore our y-intercept is not really there. This right here is not actually where our true y-axis and stuff is supposed to be. The real y-axis is like way over to the left. So, in conclusion, the bottom line is you got to be really careful about counting off your slope, which is why I just say use your formula. The formula's never fooled. And also, you also got to be really careful about, I can just see where my line is going to cross my y-axis, so I can just see it's not always that simple, because it turns out the y-intercept is not going to be 15 or 16 or whatever. Not even close. Okay? Not even close. Because without this little like skippage of x-axis, this line's going to have to keep on going and going and going and going of a pretty long time, a very long time, before it actually gets to the real y-axis. So that's why, even though I went off on that major tangent and said, hey, don't forget about y equals mx plus b, you're pretty much in much better shape to use like this formula, okay? So bottom line, use these two formulas to be like as safe and as reliable and as exact as you possibly can be. And then once you have your equation, you can make your prediction for 25 degrees by plugging in 25 for x. So what would you get here? So 16/5, like I said, was 3.2. 3.2, whoa, what's going on with my calculator? 3.2 times 25, remember I'm plugging in 25 for x, minus 92. So this answer would be negative 12, which again doesn't make any real sense. How could you have like negative 12 customers? So this data only really makes sense for certain values, because 25 degrees, the data stops making sense, you know what I mean? And just, quick idea, this is what the graph actually looks like, Like you might look at this and go, oh my gosh, like this is where my y-axis was drawn, but it's not really there. The real y-axis is way over here, so like that's why the y-intercept is actually, negative 92 was the actual y-intercept, not like 15-ish or 16-ish. The actual was, negative 92. Because without the little jagged thing, like this is what the real actual graph looks like, And let me think. I don't know if is there anything like new? Again, just to kind of predicting my students for a doctor who is 30 years out of medical school. Again, because of how the axis or both axes are scaled, you want to go with some coordinates. And this formula for slope to basically figure out that my slope is negative 1. Or in other words, like maybe, because it's in thousands, it would really be like negative 1,000, but whatever, it's not really. So we're going to use that formula. And then as far as like, where do we go from there? We have m. See, even though in this situation, like look, there's a jagged thing, but still, it's a jagged thing on this axis, 5, 4, 3, 2, 1, 0. Guess what, people? This is actually the y-axis. So if you were heads up, 7 up about this, you could actually go, wait a minute, it looks like my b value is just going to be like 136, 137, about 138. But again, like, we're probably going to go with this formula, just to maybe keep things consistent. And check it out. It turns out, guess what? Look, it is exactly the way it looked. 138 is my y-intercept, my b value, and my slope is basically negative 1 or negative 1,000, you know what I mean? So, final thing here, you could also, depending on what numbers you were using, you could say, well, it's actually like negative 1,000x plus 138,000. Like think about it. If all these numbers were in thousands, the real y-intercept you could say is like 138,000. But I like what's in purple more. Like I like having a slope, say, of negative 1 along with a b value of 138 rather than just saying what's in red. But okay, I think that does it for those 4 follow-up examples to like what's the equation of my line, make this prediction, and all that kind of stuff. All right.